Hello APC Mechanics students, today we'll solve the past paper FRQ 2010 exercise 2. A bowling ball of mass 6.0 kg is released from rest, then initially we don't have any kinetic energy. From the top of a slanted roof that is 4 meters long and angled at 30 degrees, as shown above. The ball rolls along the roof without slipping, so this is very important, which means that rotational motion is completely related to translational motion. The rotational inertia of a sphere of mass m and radius r about its center of mass is given by 2/5 mr square. Part A on the figure below, draw and label the forces, not components, acting on the ball at their points of application as it rolls along the roof. So we know that because the sphere has a mass, it will be subjected to the pull of gravity from the center of mass. So it's very important that we represent the pull of gravity from the center of mass. So that's Fg. Then we proceed from the normal push. The normal push should be represented from the point of contact between the sphere and the slanted height. So that's the normal push. And finally we have friction in the opposite direction of rotation up the ramp or the slanted height. So that's static friction. Why static friction and not kinetic? Because we have rolling without slipping. So both normal force and the static friction are being represented from the point of contact, and the pull of gravity is being represented from the center of the sphere. Calculate the force due to friction acting on the ball as it rolls along the roof. If you need to draw anything other than that what you have shown in part A to assist in your solution, use the space below. Do not add anything to the figure in part A, and this is usually known for the rigid body diagram. So we don't, or for the FBD, we don't add anything to our diagram. Now, in order to calculate the force, which means we need to implement a law, then we're gonna apply Newton's second law for rotation. But now what's our pivot point? Now, because we are interested in determining friction, so we cannot choose basically at the first glance the pivot around this point, because both friction and the normal push would be eliminated. So we need to choose the pivot or the axis of rotation to be the center of the sphere, and the surviving term would be the static friction in order to calculate it. So in this case, let me write it quickly here and show you. The equation of motion would be given by Fs multiplied by r is equal to I alpha. I here would be around the center of the sphere, and alpha would be given by A divided by r. So we're interested in determining Fs. However, A is unknown. So the first thing we do before we proceed in the calculation for the static force or the force due to friction, we need to determine the acceleration. And in order to determine the acceleration, we need to consider the pivot at the point of contact in order to eliminate both friction and the normal push. And then let's say apply Newton's second law for rotation. And initially we're gonna choose it about the point of contact. And we're gonna say torque naught is equal to I alpha. Now, what are the different forces that are acting on the sphere? We have the torque produced by G plus the torque produced by the normal push plus the torque due to the static friction is equal to I alpha. Now, these two are basically directly eliminated, because if we're working about this point, both forces, the line of action passes through this point. Now, what about the moment of inertia? We know that the moment of inertia of a sphere is given by 2/5 mr square, but according to our choice, because we're working at the point of contact, we need to utilize I using the parallel axis theorem. So that would be 2/5 mr square plus the mass multiplied by this distance, which is mr square, multiplied by alpha, and alpha can be directly replaced by A over r, because we are in the case where we have rolling without slipping. Then R, so before doing the cancellation, the torque produced by the pull of gravity. Now the force of gravity would be mg multiplied by the distance from the force to the point of contact, which is basically R. Now we need to, it's left to multiply by sine or cosine. Now why this is positive? Because the force of friction is providing torque along the direction of motion. Now we need to determine whether it's sine or cosine. That is the radial direction. So first let me say that this is the angle theta. It's fine if we add angles to our diagram. Now that's the radial direction and that's the tangential direction. If this is theta, then that would be pi by 2 minus theta. So cosine pi by 2 minus theta would be sine theta. And we always know that the pull of gravity along the acceleration always negotiate with a sine and not a cosine. And if you add these two fractions, 2 over 5 plus 1, that would be 7 over 5 mr square multiplied by a over r. Now r cancels with r cancels with r as well as m. So we're left with g sine theta equals to 7 over 5 a, which means that a, the acceleration that we're gonna use in order to find friction, is given by 5 over 7 g sine theta. And now again we're gonna apply Newton's second law for rotation, but in this case we're gonna apply it along the center of the sphere in order to eliminate the pull of gravity and the normal push, and the surviving term would be the static friction. So apply again Newton's second law for rotation. But in this case, we're gonna say about the center. Then torque net would be equal to I alpha. Now torque produced by G plus the torque produced by N plus the torque produced by the static friction is equal to I alpha. And here I have noticed that I've mentioned something which is wrong. Now here I talked about the torque produced by the static friction, which is said to be positive, but we were discussing the pull of gravity. Now also the pull of gravity provides torque in the positive direction. Okay. Now in this case, both the pull of gravity and the normal push, the line of action passes through the center, so we can directly eliminate this, and we're left with the static friction. So I will continue my work in this region. Now the static friction, as we said in the first part here, it provides a positive torque and it's being applied tangentially to the sphere. So that would be F static friction that we're searching for, multiplied by the distance r from the point of application to the center. No need to multiply by cosine or sine since it's being applied tangentially. That would be I. So what is the moment of inertia here? We're talking about the center according to our choice here. So it's just 2 over 5 mr square multiplied by alpha, which is basically a over r. Now r with r would cancel, r with r would cancel. Then the static friction in this case is given by 2 over 5 m multiplied by a. And if you notice carefully, they told us to calculate, which means that we need to achieve the numerical value. Now that would be 2 over 5. The mass is given by what? Is given by 6. And the acceleration in this case is given by 5 over 7. Now g is 9.81 and sine 30. And plugging that expression on the calculator, we're gonna find that the force provided by the static friction is given by 8.4 newtons. Then the static friction provides 8.4 newtons. Now in part C, we need to calculate the linear speed of the center of mass of the ball when it reaches the bottom edge of the roof. This is straightforward because we have the acceleration. Since it's constant, then we can use kinematics, which is basically v square x is equal to v square x0 plus 2ax delta x. Now initially we started from rest, so the speed of the center of mass, which is basically given by v square, would be 2 multiplied by the acceleration, which is 5/7 g sine theta, and delta x would represent the distance traveled along the roof, which is basically this distance. And that would be 4. Now v in this case is given by the square root of 2 multiplied by 5/7 multiplied by 9.81 multiplied by sine 30 and multiplied by 4. Plugging this expression on the calculator, we're gonna find that the linear speed at the bottom edge of the roof is given by v, which is equal to 5.3 meters per second. And now for part D, a wagon containing a box is at rest on the ground below the roof so that the ball falls a vertical distance of 3 meters and lands and sticks in the center of the box. The total mass of the wagon and the box is 12 kg. Now here pay attention, that's the wagon and the box. Both combined, they are of 12 kg, and the mass of the sphere alone is given by 6 kg. Then after the sphere sticks to the system wagon box, we will have a total mass given by 12 plus 6, which is 18 kg. After the sphere sticks to the wagon and the box, we need to calculate the horizontal speed of the wagon immediately after the ball lands in it. So immediately after the ball lands in it, we're talking about collision and the conservation of linear momentum. And here let me say apply conservation of linear momentum, which states P initial is equal to P final. Now initially only the sphere possesses momentum, so that would be the mass of the sphere multiplied by the velocity initial, let me say, and P final would be the combined mass, which is m plus m, multiplied by the velocity v that we're interested in calculating, let me say vf. Then vf in this case would be given by a fractional mass m over m plus m multiplied by vi. Now what does capital M represent? That would be the mass of the sphere, which is 6 kg, because it's the only object that possesses momentum before collision, and the small m would be 12 kg, which is the mass of the wagon and the box. So basically we know the masses, it's left to determine what is vi. Now the sphere at the bottom of the roof, it has a speed of 5.3 meters per second, but here notice carefully that we have an angle with the bottom of the roof with the horizontal. So the velocity here, if you need to represent the velocity would be something like that, which has a horizontal component and a vertical component, and the value of the velocity is given by 5.3 meters per second. But if we need to consider the conservation of momentum along the horizontal, we need only to consider the horizontal component of this velocity. And if this is the angle 30, then that would be the angle 30 as well. So because you can think about it, this is the angle with the horizontal and this is the horizontal, so that would be 30 degrees. And when the sphere falls, the only force acting on the sphere is the pull of gravity, which is vertical. So there are no forces in order to modify this value along the horizontal. 5.3 times cosine 30. So basically the horizontal component of this velocity would be 5.3 times cosine 30, and that value would remain constant while the sphere goes from the point A and sticks to the wagon and the box. So basically that is the speed that we want to use before collision. So here let me say that vi would be equal to the v that we have determined in the previous part times cosine 30, which is basically 5.3 times cosine 30, and that would be 4.6 meters per second. So that would be 6 over 6 plus 12, a fractional mass multiplied by 4.6. Plugging that expression on the calculator, we're gonna have a value of 1.5 meter per second. Then the final speed of the system would be 1.5 meter per second. And that's it for me in this video, guys. See you soon in a new one.